Okay, so we are in the final section of chapter 13 right now. This is section 13.5, and the title is Trigonometric Form of a Complex Number. So it does not have all that much to do with vectors. It actually kind of does, and also something to do with polar form as well. There's just a lot of things that are just going to common themes that run through all of these topics. But this is really interesting. So we're going back to complex numbers, remember, the standard form of a complex number is a plus bi. Oh, look at me, right in the eye like it's a vector. A plus bi, where this is in standard form, and A is your real component and B is your imaginary component of the complex number. One thing we haven't had a chance to do a whole lot of is plotting a complex number on the complex plane. The complex plane are two axes, in which the horizontal axis is the real axis and the vertical one is the imaginary axis. And so, for example, the complex number -2 plus 3i plots as a point here, where the real component, -2, is -2 units from the 0, and 3, the imaginary component, is up 3. And so this is, if I were to call this number imaginary number, or this complex number z, and this would be point z. Okay. So we're going to talk about what the absolute value is of a complex number. And the absolute value of a complex number is just its distance from the origin when plotted on the complex plane. So this would be the absolute value of z, the distance from the origin. And so we use, once again, the Pythagorean theorem in order to get that, because your real component, A, is the horizontal length and B is the vertical length. And so to get that diagonal length or absolute value of the number, you just use the Pythagorean theorem. And so here I have two examples. -6 plus 3i, that is this point right here. And to find the absolute value of -6 plus 3i, that's the distance from the origin. And so that's just the square root of 36 plus 9, or the square root of 45, which is 3 radical 5. My second example, I have a complex number. The real component is 0, and the imaginary component is 5. And so you can see that the absolute value of 5i is just 5. It's 5 units up from the 0. Okay. We're going to now talk about, that was just a little review of complex numbers. Now let's talk about the trig form of a complex number. Not a lot of people see this. It's an interesting branch of math, and it's going to be pretty fun. So we already know how to add, subtract, multiply, and divide complex numbers. But we're going to learn how to do powers and roots today. We're going to learn how to do powers and roots. So we're going to, for example, we're going to learn how to do -2 plus I to the 7th power. But before we get into any of that, we're going to relearn a way of writing a complex number. So it's another way of writing it, and that's trig form. And what I have written here are the directions, or the explanation and definition of what trigonometric form of a complex number is. So, and essentially, this is just taking the graph, the complex number graphed on the complex plane, and it is just writing that in polar form. It's writing it in polar form, where you need to know r and theta. And so that's why we see this again and again. R is called the modulus. Theta is called the argument. But the way that you would write, for example, the one we just did, -6 plus 3i, which was here. The way that we would write -6 plus 3i in trig form is to find the modulus, which is just the absolute value. So we already found that. That was 3 radical 5, right? And let me show you where that came from. That is the square root of 36 plus 9, or the square root of 45, which was 3 radical 5. And then theta, to get theta, well, the tangent of theta is the y over the x, and the y is the imaginary part, so that's b over a, 3 over negative 6. So the tangent of theta is negative 1/2, and that would give me theta equals, okay, so opposite over, oh, that's not a nice number. We'll have to use our calculator. Okay, so if you type in the inverse tangent of 1/2, you get a reference angle of, I'm going to go ahead and just do it in degrees, 26.565 degrees. But this is definitely in quadrant 2, and so really theta here is going to be 180 minus that, which is 600, well, hold on, 153.435 degrees. And so this number in trigonometric form, and I'm going to just follow this formula right here, is 3 radical 5, and we do want to write it this way. We don't want to multiply in or simplify or anything. Cosine 153, I'm just going to say 153, plus I ran out of room, sine of 153. Okay, and then my second example here is the complex number 5i. Remember 5i, we just did that one, that was up here. And you can see that the way this is going to be in trig form, well, the absolute value of the complex number, which is also called the modulus, which is that letter R, that's going to be 5. And then we're going to say, what would theta be? That's 90 degrees. So cosine 90 plus I sine 90. And I know that cosine of 90 is 0, and I know that sine of 90 is 1. And if you go ahead and evaluate these trig functions, see what happens. You get, now, and then go ahead and distribute the 5, you get 5i. And that's what we started with. So there is a good reason to write these numbers in this form, even though this form doesn't look simplified. Okay? And here I have an example in which you work backwards. And I'm going to go ahead and let you do this example. You just need to simplify the cosine and the sine and distribute the square root of 8, just like I just did. Okay, so before I teach you how to do powers and exponents of these complex numbers, I'm going to show you how the multiplication and the division works when the complex number is written in trig form. So this right here is our definition of how to multiply two complex numbers and how to divide two complex numbers when those numbers are written in trig form. And the way it works is you just either multiply or divide their modulus, and then you either add or subtract their the angles. And that's it. It's as simple as that. It's what you would want it to be. And because it's so simple, that means we can do the powers. And so in this example, what is z1 times z2? Well, notice there's no r there, but there is. It's just a 1. You're going to multiply the two moduli, so that's 2. And then the cosine will be of them added together, 150, plus I sine 150, and that's it. It's as simple as that. Yay! Now, when you divide them, z1 divided by z2, you're going to divide the two moduluses, so that's just 1/2. Cosine of, now I'm going to subtract, 120 minus 30 is 90, plus I sine, and then I'm going to subtract 120 minus 30 is 90. And that's it. It's as simple as that. Okay, so how do I do the powers? Well, a power is just a repeated multiplication. And so if you take a complex number and you multiply it by itself over and over again, then that means you're going to multiply the r by itself over and over again. And so you get r to the n, where n is that exponent. And similarly, you're going to add the thetas to themselves n times. And that's all that it is. So, and this is called de Moivre's theorem. De Moivre is the mathematician who first developed this. So if I want to find this complex number to the fifth power, it's just 3 to the fifth times the cosine of 100 plus I sine of 100. And that's it. And so you can see that was my example 1. This one is written in trig form. Number 2 here is not written in trig form. If I want to do -2 plus 3i to the fourth power, then I have to literally FOIL 4 times. That's how you would have to do this. But multiplication and division is much easier when the complex number is written in trig form. So that's what we're going to do. We're going to first change this to trig form, and then it'll be a very simple thing to do. Okay, so I need to find the modulus. I need to find r. That's the length of it, or the distance away from 0. And so that's the square root of -2 squared plus 3 squared. And so that's the square root of 13. And then I need to find the angle. So the tangent of the angle is the imaginary part over the real part, is 3 over -2. And then I'm going to type that into my calculator. Okay, and so I did that, and I got a reference angle because I just dropped the negative. I did the inverse tangent of 3/2, and I got a reference angle of 56.31 degrees. I have to think about which quadrant this is in. The real is negative, and the complex is positive. Boy, I love quadrant 2 today. That's quadrant 2. So that gives me a theta of 180 minus that, which is 120, let's just say 124. 124 degrees. And so this same complex number, -2 plus 3i, -2 plus 3i, can be written in the form radical 13 times the cosine of 124 plus I sine of 124. And so when I need to evaluate what this is to the fourth power, I can use the trig form, and it's as simple as just taking radical 13 to the fourth power. That would be 169, and then cosine of 124 times 4, which is 496, and then we're done. Whatever that number ends up being. And so I can go back to the standard form of the complex number. And I've done that now. So what I just did is I typed in the cosine of 496 and multiplied by 169. And then I did the sine of 496 and I multiplied by 169. And so now I'm back in A plus BI form. And so that's how you do powers. The last part is how we are going to do roots. And the roots work the same way. You're going to find an nth root. There are exactly n answers. So to do that nth root, you're going to, and to get all of the n answers, it's a little bit more difficult to find the thetas when you do that. Okay, so let me do an example here where I do the fifth roots of -1. Did you know there are 5 roots of -1? Normally, if we did the fifth root of -1, we would only find the answer -1, and that's because that's the only real answer. There are really 5 numbers that when you take them by themselves 5 times, you get -1, but the rest of the other 4 are complex. Okay, so let's find them all. To do this, we're going to have to write -1 in trig form. So -1, it has an r of 1 and a theta of 180 degrees, right? Because -1 is right here on the x-axis. And so now that I have r and theta, then written in trig form, -1 equals 1 times the cosine of 180 plus I sine of 180. Okay, So now to do the fifth root of negative 1 and to get all of those answers, the fifth root of negative 1, I'm going to start with, and I have to do k equals 0, 1, 2, 3, all the way up to 4. Okay, and so as I do that, I'm going to get, well, the fifth root of 1 is just 1. So at k equals 0, I have, and I'm going to try to use my definition here, I have 1 cosine of 180. And so in my first one, k is 0, so it's 180 over 1. Or no, yeah, 180 plus, I'm not going to add 360 over 1. So 180 plus, okay, so I've decided to switch to radians because it's going to be a little bit easier. But in this definition, in this definition, there are really two definitions. And this first one is for when theta is in radians. But what you're going to do is you're going to essentially just add multiples of 2 pi. Or, in the case of degrees, multiples of 360. It's just a little bit easier to not deal with such large numbers and to do the radians. So that's why I've switched. I'm going to make theta equal to pi instead of 180. And so we're going to have 5 answers here. 5 answers because we're doing a fifth root. To get the 5 answers, I'm going to use this definition 5 different times. Once for k equals 0, once for k equals 1, 2, 3, all the way up to 4. All right, and so I've started to write a shell of what these answers are going to be. Starting with k equals 0, I've just written my r1 cosine theta plus I sine theta. And I did the theta for the first one. And so the theta is what's changing in all of these answers, okay? The way the theta changes is you start with your original theta, which is pi, and you're going to divide that by the root you're taking. So we're doing the fifth root, so we'll divide by 5. And then you're just going to add multiples of 2 pi after that. And so our first one, we'll do the cosine of pi fifth, I sine pi fifth. And then the next one, we're going to take the answer, our direction pi, and then add 2 pi because k is 1. So we're going to just add 1 times 2 pi. That is 3 pi, and that's why I got a 3 pi fifths over there. And the next one, we'll add 2 pi's, or 4 pi. And so that's 4 pi plus pi over 5. So that's 5 pi over 5, which is just pi. Then we're going to add 3 2 pi's, which is 6 pi. 6 pi plus pi is 7 pi. So this is 7 pi fifths. And then in our last one, we're going to take pi and we're going to add 4 2 pi's, which is 8 pi, and then divide by 5. So that's 9 pi fifths. Okay? And then we can just find the values of all of these and put these back into standard form. Okay, and so we're almost done here. And so what I've done after I went ahead and found the trigonometric form of all of the fifth roots of -1, I went ahead and put them in standard form of a complex number, and those are these answers in black. And I just simply did that by typing in cosine of pi fifths, sine of pi fifths. The cosine of pi fifths was 0.81. And if you look at these answers, they're actually, they seem to almost follow a pattern. And it's true because remember, complex numbers come in pairs. And so if you look at this root and this root, this is a plus bi and this is a minus bi. These are complex conjugates, and all roots come, all complex number roots that are non-real answers come in complex conjugates. And so 0.81 minus 0.59i and 0.81 plus 0.59i are one set of complex conjugates, and then the other ones are these 0.3s, and then here's your real answer as well. So 5 answers. Okay, I'm going to go ahead and let you stop here. We are going to do this next example too, but we will do this first thing in class tomorrow.